Okay, we are back. Woo! Home drama. Okay, I think the last thing I was saying, maybe, is that language is in general infinite, and what I mean by that is that even given the finite number of words in the English language, there are an infinite number of grammatical sentences of that language, which is to say, you can make sentences which are sort of arbitrarily long, including stringing together sort of relative clauses. You know, the man on the log with the bat by the spider in the sunshine, etc. You know, liked the man who blah 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 blah. And so any grammar that you have to describe that language is going to have to be kind of recursive in a certain way. And so what we have is a system here in which, though our alphabet is finite and our grammar is finite, in the sense that we have a finite number of rules, and yet somehow we can generate an infinite number of valid strings. Sort of a very powerful idea. Okay, Oh, yeah, these rules, these are sometimes called production rules, or people call them substitution rules. So production rules or substitution rules. And okay, these are both good names because in some ways we are sort of producing the string, and there are substitution rules because every rule, at least the ones we're seeing here, have the form where we substitute for some character, some new substring. Okay, and I think we're also seeing. Well, actually, hold on. Before we get back to this, I thought there was one more thing I wanted to do, sort of still with this example here, and that is to produce what is known as a parse tree. So the parse tree is in some ways a kind of a snapshot of the structure of the entire string which was generated. This string was generated via this sort of sequence of applications of the rules on the left. And so you can sort of view this more in a more structured way by doing this. So you have sort of, well, okay, let's see, down here or something we have the string. The string is the cat with the flower sleeps. And now I will show the various relationships. So you have S, this becomes NP and VP, sort of splits in a kind of a way. This is more of how a linguist would draw it, except they would use correct linguistics. And this NP split into this N prime and PP. N prime is just a symbol I invented out of basically thin air for this. And this is A, this N prime rule got split into A and N. A became the, N became cat. This P became P and an N prime. P became with, N prime became an A and an N. A, N. A was the, N was flower, and this VP, I guess, we used a rule that said V prime, and we used another rule that said V, and then that became sleep. Okay, so this parse tree is a sort of fully structured description of this string, showing the precise way in which this string was generated. Okay, and if you this sort of long detour into linguistics might seem strange, but of course what we are getting to is applying this same way of thinking to constructs in computer science. And in computer science, these kinds of parse trees are extremely important when you want to parse some kind of string. And if you write some sort of code in Java or something like that, the compiler has to take your Java code and in fact turn it into some kind of structured parse tree like this in order to extract the various relationships between all the symbols in your string. And so when you are designing a programming language like Java, I don't really know what I'm talking about here at all, but you might want it to have the property that this is the sort of reverse of what we're doing, which is generating strings. You might, if you were designing an artificial language that you want it to be understood, you might want it to have the property that for any given string that there is a unique parse tree associated with that string. And so that means that the sentence is not ambiguous. And if you design your sort of rules properly and you limit the precise grammar of Java to be, for example, if you construct the syntax for Java in such a way, a good property to have, I don't know whether Java has this property or not, but it seems like it should have it, that any given valid line of Java code, what the compiler is going to do is to extract from it the underlying relationships and to produce the parse tree for that string. And it would be nice if there was a unique parse tree. Okay, so that's kind of the other half of linguistics is sort of interpreting the sentences that are uttered and to sort of recover their meaning. Okay, woo! Where were we going with this? I went into this extremely long-winded example, and I do this even in normal years when we are not learning remotely, because I think that it illustrates a good overall illustration of the sort of idea of a grammar. And a lot of this sort of, if you don't do this detour into linguistics, a lot of the sort of vocabulary doesn't make any sense. But okay, so moving us sort of a little bit away now from linguistics and more towards the formal idea behind these generative grammars. Before we do that entirely, let's just kind of look back and sort of see that if this is our grammar, that we have sort of two different kinds of symbols in our grammar, so to speak. We have all of these symbols that we created for the purposes of explaining the grammar. These are sort of theory internal symbols. These symbols are called non-terminal symbols. And, okay, I'll explain that in a minute, symbols, but for the moment, they're just the symbols that we use sort of in the background, so to speak, to analyze the grammar. They're sort of intermediate on the way to the other kinds of symbols, which are the terminal symbols. And, okay, this is the language that people use and the language that Gossett uses. What is a terminal symbol? Well, it's just a symbol, but it's a symbol which is expected to be one of the symbols of your target language. So in this case, our terminal symbols are equal to our alphabet, and that's in general true, with a little bit of an exception. And then, okay, I don't think I need to write this out. The non-terminal symbols for us are S, NP, VP, N prime, PP, etc. And the terminal symbols for us are A, the, cat, dog, etc. Okay, there's one tricky bit, which is that there's also, in addition to these terminal symbols and non-terminal symbols, there's this special character. And this special character is sort of part of the language of analyzing strings, and that is the empty string. Okay, so most people use epsilon for this, but Gossett doesn't. For whatever reason, he uses lambda. So, okay, my lambdas are kind of bad, but that's lambda, and this symbol represents the null string. And the null string is a string. It's just a string with no characters. So it's a string of length 0. And the null string comes up kind of a lot. And I would just like to sort of say, but I'll explain this again later maybe, that this null string is always one of the terminal symbols. In other words, you can think of it being like this. You can think that there is our target language. There are the characters of our target language that we're interested in, and that's the alphabet. And when we go to the goal of the grammar is to generate combinations of the elements of this alphabet into sentences. And for the purposes of our grammar, we introduce new symbols. And the non-terminal symbols are non-terminal in the sense that we're not done with them or something, right? The string, we finish generating the string when we have reduced all of the non-terminal symbols to terminal symbols. Okay, I erased it, but we did 2 of these, and you saw how the generation of the string proceeded with lots of non-terminal symbols, and sort of one, by following the rules, we eventually get down to replacing those non-terminal symbols with terminal symbols. So the terminal symbols are just the characters from the alphabet. But we also think of the null string as a terminal symbol because it's one of the things. Well, I'll just leave it at that for now. Okay. So I wrote all this stuff down. So I think I should read it. The production rules. That's what these are. Replace non-terminal symbols with a string of terminal every one of these production rules has the format of a certain non-terminal symbol is replaced with some kind of combination of non-terminal symbols and terminal symbols. That's what every one of these rules has in common. And a string is generated when there are no more non-terminal symbols left to replace. So therefore, when the entire string consists of just terminal symbols, then we've finished producing that string. And I'm just saying these all out loud now. The sequence of substitutions, okay, I erased it, but the sequence of substitutions, starting with S and ending with the string of purely terminal symbols that's in the target language, that's called a derivation. And the set of all strings is called, that a certain grammar generates, is called the language of the grammar. Maybe I should write some of this down. So the sequence of substitutions from S to a string in the target language, to a string in the target language. For example, one of our sentences above, I erased those two, but our example 3 is called a derivation. Is called a derivation. And the other sort of piece of vocab is the set of all strings that a grammar generates is called the language of that grammar. Okay. The language of the grammar. So given a particular grammar, then the language of that grammar is the set of all strings that grammar generates. Okay. And in fact, given any sort of non-trivial grammar, it will always generate an infinite number of strings. And so in general, though the alphabet, or the set of terminal symbols, which is basically the same thing, is finite, and though there are a finite number of production rules, the language is in general going to be an infinite number of strings. Okay, good. That was something like the half an hour mark, which is kind of how long I thought it was going to take. I think this is important sort of context. I don't know, I hope you watched on 2 times speed and learned something from all of this. Otherwise, the sort of language of terminal symbols and non-terminal symbols can seem kind of silly or weird or artificial or something like that. So we have now so now we're sort of starting. We're going kind of back into and following along everything that Gossett does in section 9.3. And there's just a lot of material in this section. This is his section. This is an introduction to formal languages. And the idea is, okay, I kind of said all this already, right? But you have sort of some algorithm in your mind. You translate that algorithm into Java code, and then I said all this already. Okay, so this is, Gossett even mentions that this is sort of the motivation for this study is ultimately this kind of thing that we're learning right now is the thing you need to learn if you are going to understand compilers or write compilers or work on compilers. That's the computer science perspective. I think I mentioned that already. Okay, so this is going to be a little bit repetitive, but now forget about linguistics. That was the sort of motivating example. Now let's get right down to sort of more abstract computer science contexts. And okay, so we're going to do some vocab and some examples and stuff like that. So like I said before, this sigma thing is called the alphabet, and it is, in fact, a finite, non-empty set of characters. So that's what we call them, the characters. Some people will also call them symbols, but I will probably mostly call them characters. And this thing, I personally call this the alphabet. I think that's the good word to use. Okay, and any finite string of characters is a word. Characters is a word. In our linguistics examples, the sort of smallest units were in fact already words, and the string we were making was like a sentence. But if we're studying this abstractly, it's more simple to think of this alphabet as being composed of sort of single characters, and then any string of those characters we call a word. So word is the word that Gossett will use to refer to this. But, okay, also owing to the influence of linguistics, some authors will also call it a sentence. Okay, good. Then we have this null string. So lambda, this is the bad lambda, is the null string, as I already mentioned. And it contains no characters. So, so lambda, yeah, lambda contains no characters. But lambda is a word. Lambda is a word. Because a word has been defined as a finite string of characters, and lambda is a finite string of characters. It's just a string of length 0. Okay, so, and now I'm sort of clarifying something I think that Gossett really messes up and which leads to a lot of confusion every year. And if I was doing this in class, I would sort of let the confusion happen and maybe then address it later. But given some sort of alphabet, I'm just inventing this notation now that's slightly different from Gossett, but it's basically the same. Let's just let, actually this star is a terrible notation. Oh no, sorry. This is still his notation. Given some alphabet, let sigma star be the infinite set of all finite length words, of all finite length words, using symbols from that alphabet. Using, I'll say, characters from sigma. Okay, so given some set of characters, I now invent this new, I introduce this new notation, sigma star, Gossett introduces it, to refer to all possible strings composed of characters from that particular alphabet. Okay, and so a language over that alphabet, we say, a language over sigma is a subset of sigma star. So what is a language? A language is just a set of strings. But specifically, it's the set of strings drawn from some particular character set. So if you give me all this is saying is, you give me some alphabet, and then some set of strings consisting of some set of strings which all of those strings contain only characters from that alphabet. We call a language over that alphabet, and it's just going to be sum of the set of all the possible strings you can make using those characters. Okay, let's do an example right now that's more in the line of the sort of theoretical kind of examples that we're going to be doing for the rest of this unit. So I will now introduce some alphabet. So let sigma be ABC. Okay, so this is just these 3 characters. All right, well then, what just immediately now I say, well, what is sigma star? It's difficult to write this, but it's every single string that you can make out of the letters ABC. So it's the empty string, it's just A, just B, just C, A, I guess I should say, A, B, A, C, B, A, B, 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 C, etc. And it's going to be infinite because the words have arbitrarily long length. But all the strings are finite. So every string is finite, but there are an infinite number of them. Okay, good. Now, consider the following language. Consider the language L. And L is all the strings W such that W starts with A. Maybe I'll just say starts with A, ends with C, ends with C, and has 0 or more B's in the middle. Okay. All right. So, starts with A, ends with C, and it has 0 or more B's in the middle. So, for example, man, running out of space here. Well, I guess we're okay. For example, what does this language L look like? Well, it has to start with an A, it has to end with a C, and then, okay, I think this is pretty easy. It's A, C, A, B, C, A, B, B, C, A, B, 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 C, etc. Alright, and I think I now understand this language, and what I would like to do is to write a grammar which generates all the strings of this language. And I think this is quite easy to do. So we have some sort of start symbol, which you can think of as referring to start symbol. That's what people call it, but I think it's etymologically goes back to sentence. I could be wrong about that though. And okay, well look, if every string has to have an A in it, then first let's just kind of like make an A. But then also, I have to make some B's, but possibly none. So let's create a temporary symbol, a non-terminal symbol, that's acting kind of like the sort of noun, verb, phrase, V prime, PP, whatever symbols we're acting in our linguistics example. And let's think of sort of B as, I'm about to make some B's now. And then B can be replaced with, well, you want your grammar to be powerful enough to generate strings with an arbitrary number of B's in the middle. So, so you want to be able to make some B's and then kind of like go back to the business of making more B's. But then when you're done making B's, you want to just stop and you want to close this off with a C at the end. Okay, I think this example is easy enough that you can just readily see that by following these rules, starting with the start symbol S, I have to explicitly tell you that you need to start with this symbol, that this is going to produce basically all of the strings of this alphabet. And so what I want to be true is that if I call this grammar G, that the language of this grammar is in fact this language L. Okay, and I think we sort of did that. Alright, while we are at it, why don't we explore something which is very tempting, which is kind of a preview of what we're going to do next week, but we really should start talking about it now, which is all this talk of I'm going to do B's now or something like that. It reminds us a lot of states. And in fact, there's this deep relationship between these grammars and finite state machines. So I think that this language is also simple enough that I can create a finite state machine for it. And so let's do that. Well, I need some states. And so I'll make a start state. Well, the start state, I'm kind of, I'm just sort of not that happy or sad because I need my string to be of the form A, some B's, and then a C. But so far nothing has happened, so I have no emotion. This is, my daughter calls this just okay face. Okay, but what would make me happy is if an A came next. If an A came next, I would be happy. Because that means that we're on our way to having a string which is valid. And then, after this A, what can come next? Well, what can come next is a B, or not, or 2 B's, or 3 B's, or a million B's. So I stay happy as long as my finite state machine is reading B's over and over again, I stay happy. And what would make me really happy? so happy would be if this were a C. And here I go to the love state. This is a new thing I just came up with this year, which should be an accept state. Because if the string looks like this, I want to accept it. Right? Okay, good. However, some more complicated things can sort of go wrong. In particular, what happens if I don't read an A first? Well, this string has to start with an A. And so if anything but an A is the first character of this string, then I need to go to the sad place and never leave. So if I read either a B or a C, then I need to go here. And now I need to consider every single possible case, because of course I'm not done with the finite state machine until I have given a rule. Since I've told you that sigma is ABC, it means that I need to have a rule for what to do in each state for each one of those possible inputs. So what's the other thing to worry about is that if I'm here at B, what if I should read an A? Well, if I read an A here, then I automatically go here. And this string needs to end in precisely one C. So if I made it all the way here, it means that some A's happened, then, if one A happened at the very beginning of the string, then some B's happened, then one C happened. But if anything else should happen, I should go to the sad place. And once I'm in the sad place, you just never leave again. So I also need to give directions for what to do in the sad place. And in the sad place, regardless of what I read subsequently, I need to just stay sad forever and in fact die there. So there's only one path, and if I've done this correctly, there should be 3 arrows precisely coming out of each one of these states, and I think I just have done it correctly. Okay, so it seems that when it comes to talking about this language, I have 2 options. I can write a grammar which generates the strings of that language, or I can write a machine which recognizes it.